Hello everyone, Mr. Minix. My name, math is my game. Here at school on today, doing things a little bit different. We're experimenting with this block scheduling because of the air test. So today we're looking at chapter 6, section 3. The title is Binomial Radical Expressions. Binomial Radical Expressions. Probably one of the most complicated sounding titles of anything we've studied to date. Binomial radical expressions. Ironically, the direction, the instruction, the advice that I'll give to you on today is going to sound as if I'm a Valley girl, and I don't mean any disrespect to any Valley girls or anyone who speaks like that. But I could sum this lesson up in one statement. I'll say this: like radicals are like terms. And when I say the word are, pirates like to say are a lot. Maybe I shouldn't say are. Maybe I should say, replace that with the word behave. It's kind of weird to talk about terms and an expression behaving a particular way, but that's really what they're doing. They're behaving a particular way. So that's really the gist of the lesson in a nutshell. Like radicals, that's what this is all about. Some like radicals can be combined. Well, like radicals can be combined, just like terms can be combined. So if we have like radicals, you can combine them. You can add them by adding their coefficients and keeping the back half the same. So an initial example we might see of this is this. Example 0. Simplify 6x minus 4x cubed plus 5x squared plus 3x minus x squared. So if you look at that expression in chapter 5 when we studied polynomials, we did stuff just like that. And we looked at that and we said, okay, so our term with the biggest exponent is negative 4x cubed, and that term probably ought to be written first. So we would start off by writing negative 4x cubed. And then when we look at our 5x squared term, we might realize, hey, this 5x squared term has another term with the exact same variable. And what else? The same variable and the same exponent. So that's the deal with like terms. In case you don't know the definition of like terms, whoa, shouldn't have done that. The definition of like terms is that they are terms with not only the same variable or same variables, terms with the same variable or variables, and the same exponents. So like terms, if you don't know, they're terms that have the exact same variables and the exact same exponents. So in this case, with this 5x squared and this negative x squared, both of those have the variable x, and the exponent on that variable is a 2. So we can combine those. And when we do, what's that going to make our next term look like? Plus 4x squared. Nice, good. So plus 4x squared. And then lastly, but certainly not leastly, we look at this 6x. It has a variable x, and that variable x is being raised to the, we don't write the 1, but it's really being raised to the first power. And over here, this 3x, that x is also being raised to the first power. So those are also like terms. So what's our final term then going to be when we simplify this? Plus 9x plus 9x. Okay. So that's stuff that you've been doing since 6th or 7th grade. The only thing that's going to make this any different now is the back half of it's going to look a little bit more involved. It's kind of like going to the fair. Has anybody ever gone to the county fair and looked at the exhibits, the art exhibits? And you look at the art exhibits that the 5-year-olds do. And you look at the art exhibits that the 6 to 10-year-olds do. And you look at the art exhibits that the 11 to 13-year-olds do. And then you look at the professional art exhibits. And along the way, things get more and more and more complex. Does that make sense? It's the same thing here. So here we go. Example 1. Example 1. Simplify the square root of 2x minus the square root of 3x plus the square root of 2x plus 5 square root of 3x. So it's kind of interesting here. This first term, I don't know how much you remember from last week or the week before, but that first term, what we've got going on there is the quantity 2x, and it's being raised to some particular power. Anybody know what power that particular term is being raised to? Yeah. It's to the 1/2 power. Nice. So that's why I can make this statement that like radicals behave like terms. Because really it's the same thing going on. We have variables or variable expressions being raised to powers, and their powers have to be the same. Does that make sense? So if we look at that next term then, we have 3x. So here's 2x being raised to the 1/2. Here we have 3x, and 3x is also being raised to the 1/2, isn't it? So here's my question to you. Are these two terms like? Why or why not? They're not. Why not? Because the coefficients are the same. And because these things, and I know the coefficient's not a variable, but the deal is this coefficient of 2 and this coefficient of 3, because they're kind of like embedded under a square root, the deal is they're kind of acting or behaving as if they were a variable. Okay, so to make things as clear as I possibly can, the first and second terms in that expression are not like terms. We cannot combine them. Is everybody clear on that? Okay. So the deal is if you're working with radicals, not only does the index have to be the same, not only do we have to have the same number in here, as our index, not only does our index have to be the same, but also the radicands have to be identical. Okay. So let's see if we can simplify this then. Is there anything that can be combined with that square root of 2x? This other square root 2x, right? So it's as if we have one red bicycle and we have another red bicycle. If we have one red bicycle and another red bicycle, then what do we end up with? 2 red bicycles, but our red bicycles are represented by the quantity rad 2x. Maybe I should have said blue bicycle since I used blue marker. It's kind of confusing. All right, so let's look at the next terms then. Minus rad 3x and plus 5 rad 3x. Are those like terms? They are. Their coefficients are different, but that's okay. The back half's the same. So when we combine those, what's that going to make our next term in the expression? It's going to be negative 4 rad. And here's where it gets tricky. We're dealing with what do you want to call these square root of 3x's? You want to call them ice cream cones? We lost an ice cream cone and we pick up 5 more ice cream cones. So do we now have brownies or double cheeseburgers? No, we're dealing with ice cream cones. So we're dealing with ice cream cones. We have 5 and we take 1 away from 5, so we're going to have minus 4 ice cream cones. Okay. So the deal is the radical stuff stays as the radical stuff whenever we're combining by addition or subtraction. How are we feeling about this so far? All right. Questions, comments, concerns, shorter, long debates? Okay. Let's try example 2 then. Example 2. Simplify. I like this next example. Let's go with 3 rad 8 plus 2 rad 50 plus 5 rad 2. I don't know what it is about math, but I really like it. And one thing, if you're simplifying these, you ought to think to yourself, well, there's one of them that's already simplified as much as it can be. So if I had to guess, since they're putting this kind of problem on this exercise for me to try, I'm guessing that the other terms are probably going to have some kind of rad 2 in them. Anybody ever lead off of a base when you're playing baseball or softball? It's kind of like the same thing. Because of that rad 2, I'm assuming that this is probably going to end up being some kind of rad 2 also. Maybe it's not, but I'm guessing it is. So let's look at this rad 50. What's that going to turn into? That's 25 and 2. That's really rad 25 times 2. And we know what the square root of 25 is. That's 5. So that ends up being a 5 rad 2. Just the rad 50 ends up becoming a 5 rad 2. Now don't forget that there's a 2 out front being multiplied by all that still, right? So collectively, that whole second term then ends up being what? 10 rad 2. Nice. 10 rad 2. So we have 10 rad 2. 5 rad 2s being added to that. And then out front, let's see what we got out front. With this, I guess this rad 8 is going to be rad, 4 times 2, which is 2 rad 2, but that's really being multiplied by 3. So what's that front term going to look like? A 6 rad 2. So if we go ahead and combine all that, 6 bananas, 10 more bananas, and 5 more bananas, what do we end up with? 21 bananas. Notice it didn't become 21 oranges. It didn't become 21 fruit smoothies. So far, so good? All right. I don't know who always asks the question, but somebody always says, well, is it going to get any more difficult? Of course it is. You know how we roll. By example 4 or 5, you're like, dude, I was good example 0. I was good example 1. I was good example 2. What the heck happened between 2 and 5? All right. Here we go. Example 3. Find the product and simplify. I got skills in multiplying, and I'm losing control. All right. Wow. So there were some properties that we studied last week that we said if we have some square roots, that the square root of a product can be thought of as the product of each individual thing under a radical, right? Remember that property? That's going to come into play. So this first distribution, we're going to have rad 10 times 20. Rad 10 times 20, or rad, what is 10 times 20? 200. And we got to go back to chapter 4 and be able to simplify that radical. Remember, when you simplify radicals, you're trying to find the factors of that number who have the biggest perfect square in them. And we run across them pretty quick, don't we? So what does rad 200 end up looking like then? 10 rad 2. Cool. Good. So that ends up being 10 rad 2. Now, maybe we'll end up with some like radicals in this. Maybe we won't. I don't know. I don't think we will, but you never know. This next distribution here, we're going to have plus rad 10 times 15, or plus rad 150. So again, we got to be good at finding factors of numbers. Does 150 have any perfect square factors in it? Doesn't look like it, does it? Maybe it does. 4 doesn't go into it. 5 does 30 times. 3 went into it 50 times, so 6 is going to go into it half as many times as 50. So 6 and 25. Hey, there's our pair, right? So what's that rad 150 going to become? 5 rad 6. Good. Awesome. Awesome. So that's going to be plus 5 rad 6. Do we have any like radicals at the end? No. So that's it. We have 10 garbage trucks and 5 Corvettes. We can't make that 15 jet skis. I don't know where this stuff's going into my head. How do we feel about multiplying like that, right? Okay. So that's the product of a monomial and a binomial with radicals. There's this one social studies teacher in our building. I love him. He's a great guy. And every time I call him up, I say, "How would you do this?" He says, "Use the FOIL method." So here we go. We're going to use the FOIL method. Find the product. So we're going to have rad 10 plus rad 7 times the quantity rad 2 plus rad 7. Sometimes you're going to end up with like terms. Sometimes the radicals might end up going away. So when we use the FOIL method, our first product is going to be rad, rad 20 or 5 rad, or is it 5 times 4 or 2 rad 5? So let's not get too far ahead of ourselves. It'll be rad 20. So that's going to be what, 2 rad 5 then? Cool. Good. So that takes care of the F part of foiling, the product of the first terms. The O part of foiling is the product of the last terms. So that's going to be rad 70. I'm trying to think of 70's factors, and I don't think there's any perfect square factors bigger than 1 in it. The biggest one might be 4, and 2 times 35, but yeah, 4 is not going to work. I think that's rad 70 is just going to stay rad 70. So the inner product is going to be rad 14, and that can't be simplified. And then at the end, something weird happens at the end. This kind of reminds me of Jim Carrey in Ace Ventura, Pet Detective. Remember the one where he goes to Africa, and they talk about guano, and he's in the tribe with the Africans, and they call him, I forget what they call him in the African language, but they call him white devil, white devil. I don't know why this reminds me of that. Because the last product is, the L part is going to be rad 7, which is rad 7 times 7, which is rad 49, which ends up being what? Just 7. And I forgot a square root on this third term. That's my bad. That's a neck. Did you hear that? I necked myself. So finally then plus 7. Now somebody might ask themselves, does it matter what order I write those terms in? The 2 rad 5, the rad 70, the rad 14, and the 7. Does it matter what order I put those in? I've never seen in any textbook where it's important. There's this thing called the commutative property of addition. Most of your teachers probably didn't pronounce it that way. I pronounce it that way because we live in Northeast Ohio and we have sinus problems. And some people say, it's a commutative property. What'd you say? The commutative property. Where's the N come from? There's no N in it. It's a commutative property. It's not the commutative property. It's the commutative property. There's no N in that word. The commutative property. Anyway, if you want to put these in order, perhaps you'll put the smallest radical term first. So maybe 2 rad 5 first. And then maybe rad 14 next. And then rad 70 next. And the constant, I don't know. Does the constant go up front or does the constant go in the end? I don't know. I honestly don't know. And honestly, I couldn't care less either. You know, there's a lot of things that people say the wrong way. I could care less. No, you couldn't care less. Think about it. People say things wrong all the time. I do. I say things wrong all the time. Apparently, this word, there's only one way to pronounce it according to our former science teacher. Thou shalt pronounce that word applicable. I pronounce it applicable. Applicable. Anyway, are there any questions, comments, concerns, short debates about example 4? Cool. So there's this idea that we studied prior to the midterm when we talked about conjugates. And I don't know if you remember the deal with conjugates. But conjugates are where we have a real similar expression to each other, and there's a subtle difference. We studied these back in chapter 4, section 8. We said, if you take a plus bi, that's a complex number, right? and you multiply it by its conjugate. Anybody remember what its conjugate's going to look like? A minus bi. Good. And so we could do some magical mathematical stuff. That's actually just the FOIL method. We could FOIL that out, and we'd get a squared plus, nope, minus abi plus abi minus b squared I squared. And I don't know if you know this or not, but abi and negative abi cancel, right? And does anybody remember what I squared really is? It's -1. So this ends up being a squared plus b squared. It's not important that it's a squared plus b squared. What is important is that the I goes away, right? So when you multiply a complex number by its conjugate, the number's no longer imaginary. It becomes for real. So the same thing's going to happen if we take a couple of radical numbers and multiply them by their conjugate. Whether they're both radical or whether just one of them's radical, the same thing's going to happen. So let's see what's going to happen here. Rad A, oh gosh, dang it, I didn't find the conjugate, did I? What I got? That's got to be a minus, right? Okay, so what's this going to look like then? It's going to be rad A times A, or just rad A squared, which is just A out front. And then it's going to be minus rad ab plus rad ab, and the rad abs are going to cancel. And then on the end, it's going to be minus rad bb, or rad b squared minus b. So if you multiply a binomial radical expression by its conjugate, the product, bless you, the product is no longer irrational. Bless you. Now let's suppose we had one radical thing and one not radical thing. Do you want the A to be radical or the B to be a radical? Doesn't matter. Take your pick. A to be a radical. So rad A plus B times rad A minus B. Let's see what happens here. Out front, we're going to get what? Just A. And then we're going to get minus rad A times B. And then we're going to get plus rad A times B. So those cancel. And then what do we get on the end? Minus B squared. So it's still going to end up being rational. Capiche? Cool. We're almost done. We're almost done. I better take a look at the homework and make sure that there's not one of those kind in the homework. Not that. There'll be that in the homework. Oh boy, you guys are very, very fortunate to have the ones you have in the homework tonight. I don't see anyone. Oh, no, there is one with the fraction. Okay, so we're going to have to do that. There's one with the fraction. Those are the nasty ones. So where are we at? Example 5? Okay, we're almost done. Example 5. Find the product. So let's go with 7 minus rad 8 and 7 plus rad 8. So I know some of you are looking at that rad 8 and you're like, well, that's 2 times rad 2. You're right, but sometimes it pays to not simplify something first. Sometimes you're better off not simplifying it first, if that makes sense. You picking up what I'm putting down? Because you're just going to make more work for yourself later. It's kind of like if you had to move a pallet of bricks. Imagine if you had a nice stack of bricks, all bundled up, wrapped up, tied up, secured, and you had to move them. Now, if you had a forklift, you could take the forklift and move the whole pile at once. And if you had a forklift and you unbundled them and you put like 15 of the bricks on the ground, that's just going to make more work, and that's kind of what this is like. So anyway, let's go ahead and multiply this. The first product is going to be what? 49. What happens to the inner stuff? It goes bye-bye. So we're going to have minus, plus 7 rad 8 and minus 7 rad 8 that goes bye-bye. And so on the end, what do we get? The square root of 64, which is 8, and it's going to be minus 8 then, right? So what's our final answer? 41. Sí, muy bien. What do you think? So far, so good? Okay. Well, take a deep breath. If you have some coffee, you might want to take a little swig of that because this last part is tough. I'm not going to lie. I don't know if you remember from the other day ago when we had something like 1 over rad 2, how we had to turn that into rad 2 over 2 because radicals in the denominator are bad. Well, we're not just going to have a radical in the denominator. We're going to have a radical expression in the denominator. So it's imperative that you understand that when you multiply a radical binomial by its conjugate, that ends up making something rational. So here's kind of the trick then. Here's the deal. Suppose we have something like 5x divided by 1 plus rad 2. You're going to be asked to simplify this. The deal is the denominator has a binomial radical expression in it. And we need to get the radical out of the denominator. And it's not just a matter of multiplying by rad 2 over rad 2, because if we do that, we'd have to distribute that into both of these, and we're still going to have a radical in the denominator, right? So we're going to have to multiply by the denominator's conjugate. Yeah, we're going to have to multiply by the denominator's conjugate over itself. So what's that going to look like? 1 minus rad 2 over itself, right? Cool. So let's see what happens. Let's go straight to the denominator. The denominator is going to be 1 times 1, or 1, minus rad 2, white devil, minus rad 2 times 2, minus rad 4, or minus 2. So 1 minus 2 is negative 1 in the denominator. Okay. If you missed that, where the denominator come from, let me put up a thought bubble, because that was an awful lot going on. The denominator there was really 1 times 1 minus rad 2 plus rad 2 minus rad 2. So that stuff cancels. So that's 1 minus rad 4, 1 minus 2, and that's where that negative 1 comes from. Okay. So the numerator, I guess we just got to use the distributive property. What's that going to look like? 5x, and then minus 5x rad 2. Now, one final thing about this, math people hate writing fractions that we don't need. We don't need to put it that it's over 1, do we? Now, we got to be careful with that negative. We could stick the negative out front, but if we do, we have to put a quantity sign around that, right? Like that. Whoop, I forgot the x. So that would do it, right? If you don't like a negative quantity, maybe you want to distribute the negative through. It would just be the same thing to have it as minus 5x plus 5x rad 2. That would be fine too. Questions, comments, concerns, short debates. There's one kind of example I left out where we mix the indices. Do we want to do one of those, or you think you got it? Got the idea on these? Well, that's it. It's been real. It's been fun. I hope those of you who are working on this assignment get a chance to figure it out. Ask questions if you don't get it. And I'll see you next time. Have a great day. Good.